how different muscle movements use those sources differently. Okay, so if you're doing light intensity exercise, if you're walking, if you're lifting a light load, right, or talking, you are going to use primarily oxidative phosphorylation as your source of ATP, okay? Light intensity exercise uses oxidative phosphorylation as the source, the major source of ATP. But there's an initial time, the first 30 minutes of light intensity exercise, where anaerobic glycolysis is contributing or is breaking down your stored glycogen, Okay, remember we said that glycogen is the storage form of glucose. This is how muscles put glucose away in a reserve. So because you have that reserve glucose, you're going to break that down for the first 30 minutes of light intensity exercise, and then you're going to move to oxidative phosphorylation. Now, why is it that you can use oxidative phosphorylation for light exercise? We said that it required something. Oxygen, good, oxygen. So you have to be able to maintain adequate oxygen input in order to maintain the use of oxidative phosphorylation. I'll say that again. You have to be able to have a conversation. This is why when you're doing light intensity exercise, you can still maintain your breathing rate, so to speak, okay? Because you can still bring in oxygen and you can fuel oxidative phosphorylation for this process. Okay, this is going to increase your ventilation, increase your heart rate, your rate of muscle contraction, as well as dilate some of the blood vessels that are going to those muscles. And we're also going to increase GLUT4. Now, what is GLUT4? GLUT4 is a transporter, right, that sits in the membrane of muscle, and it allows the movement of glucose from the blood into the muscle fiber. So because you want to start using some of that glucose, you're going to increase the position of GLUT4 on the sarcolemma or on the muscle membrane. Okay. Now, if we look at this graph, we'll see that the very first curve here is that transient amount of ATP, or that transient source of ATP from creatine phosphate. Okay, it's not going to last very long, about 15 to 20 seconds, and then it's going to drop right off. Then we'll see that anaerobic glycolysis will take over, and that's going to break down the reserve of glycogen that we have in the muscle. Okay, and then the metabolic process that's really going to take over after that 30 minutes is oxidative phosphorylation. And this is specifically for light to moderate intensity exercise. All right, when we look at heavy intensity exercise, this is running, this is heavy lifting. Okay, this is vigorous jogging. Okay, the main source or the important source for ATP is going to be anaerobic glycolysis. Okay, during high intensity or heavy intensity exercise, we usually cannot maintain oxygen inflow. And because we cannot maintain oxygen inflow, we cannot rely on oxidative phosphorylation. It becomes less important here. Okay, it is still being used somewhat, but nowhere as near as anaerobic glycolysis. Now, because glycolysis produces pyruvate, and again, this is something you should have already studied. Glycolysis breaks down glucose to form pyruvate, and pyruvate can do two things. It can enter the Krebs cycle, or the TCA cycle, or if it's being produced too fast, it's going to turn into lactic acid or lactate. Okay? Now, in the case of muscle contraction, the rate that we're breaking down glycolysis during anaerobic glycolysis is too fast to keep up with the Krebs cycle. So this pyruvate gets turned to lactic acid. And this is the price that we pay for anaerobic glycolysis. This is why when you're doing these strenuous, high-intensity activities, you get that burn in your muscle. That's the lactic acid building up and giving you that burn. Another important thing about anaerobic glycolysis is that it's not very efficient. Okay, it's only going to produce about 2 molecules of ATP per glucose. Okay, whereas oxidative phosphorylation is going to give us much more ATP for much longer than anaerobic glycolysis. Okay, both of these processes have their advantages and disadvantages depending on the type of muscle that we see them in and how they're being used, what type of activity we're doing. If we're doing something light, right? You want to utilize your oxidative phosphorylation. If you're doing something heavy, you want to utilize your anaerobic glycolysis, and you're going to pay that debt, which is the burning of the muscles, the buildup of lactate. Okay. So everything we just discussed was sort of to help us look at what we're going to talk about now, right? The difference in muscle fibers. This is where we apply what we just talked about. So there are 2 basic parameters for classifying muscle fibers. We can classify them on the velocity of their contraction, how fast they're contracting, right? How many cross-bridge cycles per second. Or we can classify them on their primary source of ATP, okay? If they're oxidative fibers, their primary source of ATP is oxidative phosphorylation. This is going to require oxygen. If they are glycolytic fibers, their primary source of ATP is going to be anaerobic glycolysis. Okay, this is going to fatigue easily. Why? What is building up? Lactic acid. Okay, lactic acid. So based on these 2 parameters, we can classify or describe different fiber types. Okay. First, we'll look at the rate of contraction or the speed of contraction. Now, whether or not a muscle fiber contracts very fastly or contracts slower is going to depend on the myosin ATPase activity. There are 2 types of myosin heads, or 2 types of myosin ATPase activity. There's a fast myosin head, right? That's going to contract very rapidly. That's going to form a lot of cross-bridge cycles per second. Okay? And then there is a slow myosin head, and that is going to be found in slow fibers. That's going to contract much slower. It's not going to give you as many cross bridges per second as your fast myosin head. Okay, so let me say that again. You have 2 types of myosin head with 2 types of myosin ATPase activity. There's a fast myosin head that contracts rapidly. That's going to be found in your fast twitch muscles. There's a slow myosin head that contracts very slowly. That's going to be found in your slow fibers. Okay. Now, when we compare the fast to the slow fibers, we're going to see 2 things. Fast fibers are going to contract many times, 2 to 3 times more rapidly than your slow fibers do. Okay. So they're going to contract faster. And when I say contract, you should be visualizing what happens with cross-bridge cycling. That myosin head reaches up, grabs actin, drags it to the M line. It's going to be doing that at a much faster rate if it's a fast myosin. Right? The second thing we'll see is that it relaxes faster. Okay? And what is the step that's required for muscle relaxation? What is that one step that's required for muscle to relax in terms of the cytoplasm? Come on. I'm hearing it. Calcium. Right. Perfect. Perfect. Thank you. Calcium has to be actively pumped out of the cytoplasm back into the sarcoplasmic reticulum. So in order for a muscle to relax quickly, it has to have a faster calcium ATP pump. And these fast fibers have that. Okay, they have a faster myosin head activity and a faster calcium pump activity to actively pump that calcium out of the sarcoplasm. So they contract faster, they relax faster. Slow fibers, on the other hand, are the opposite. Okay, they're going to contract 10 times slower than your fast fiber. Okay, so if you had a fast fiber that was doing 100 cross bridges per second, your slow fiber would only give you 10 cross bridges in that second. Okay, they are much slower in their rate of contraction than fast fibers. All right, so here we have 3 graphs which depict 3 different muscle types, right, with those different fibers. So our extraocular muscles, that graph in red, that's going to contract in about 7 to 8 seconds. It'll get to its peak tension. Okay, the maximum force that this muscle can generate will get there in 7 to 8 seconds. Okay, that's your extraocular muscles. Those are muscles of your eyes. Okay, these move very quickly. They don't have to work for very long, but they need to be very rapid in their movement. Then there's the gastrocnemius muscle. Okay, it's not as slow as the soleus muscle, but it's much slower than the extraocular muscle. Okay, so it's going to have somewhere in between an intermediate fiber. Okay, then there's the soleus muscle. This is going to have very slow myosin ATPase activity. This is your, where's the soleus muscle? Anyone? Where's the soleus muscle? The soleus muscle? It's going to be in your calves, right? So right underneath or deep to your gastrocnemius, right? That's going to be an important muscle in your posture and standing and maintaining your balance. And this muscle has a long, steady, slow job to do. It needs to be able to contract for a long, slow, steady amount of time. And so its contraction rate is much slower. Okay? And again, these contraction rates have to do with fast myosin versus slow myosin. All right, so the next thing we're going to talk about was that second parameter. So we said we could distinguish fiber types based on whether they were fast or whether they are slow. We also said we can distinguish them on their primary source of ATP. Okay. So the oxidative fibers versus the glycolytic fibers. The oxidative fibers used oxidative phosphorylation. The glycolytic fibers used anaerobic glycolysis as their main source of ATP. So let's start by looking at the glycolytic fibers, and let's describe them. First of all, as the name implies, their main source of ATP production is anaerobic glycolysis. This is the breakdown of glucose, right? And this is going to cause a buildup of lactic acid. Now, these fibers are going to have fewer mitochondria. Why? Why would anaerobic or glycolytic fibers have fewer mitochondria? Good, thank you. That's used for oxidative phosphorylation. That's the site of oxidative phosphorylation. We don't need that organelle in excess here because we are not primarily depending on oxidative phosphorylation for ATP here. Okay, so we don't need as many mitochondria. We have fewer mitochondria here. There are many glycolytic enzymes. Why? Because glycolysis is the main source of ATP. So it only makes sense that you have lots of those glycolytic enzymes, right? Your phosphofructokinase, all of those glycolytic enzymes that create that step, those steps of glycolysis. You want to have lots of those enzymes because glycolysis is an important metabolic process for these fibers. Now they're going to have lots of glycogen stores, which only makes sense again. You are breaking down glucose as the main source of ATP here, so you need to have a ready supply of glucose stored, which is glycogen. Okay? They use little oxygen and they are anaerobic. Okay? Again, they are not relying on oxidative phosphorylation, so they do not need to have oxygen, which means that they are anaerobic. okay? And this is also going to be important in their diameter because they don't need that diffusion of oxygen. These fibers are bigger in diameter. If they relied on oxygen, they would need to be smaller. So there was a smaller distance for the diffusion of oxygen. But because they are not reliant on oxygen, they have a larger diameter. They're bigger fibers, okay? And lastly, they are quick to fatigue. And what was the one component of anaerobic glycolysis that led to the quick fatigue of these muscle fibers? Right, the lactic acid buildup. They're relying on glycolysis. Glycolysis produces lactic acid. That's going to build up in these fibers. They're going to be quick and easy to fatigue. Okay. Now, in terms of this image, those are going to be your white fibers, and we're going to explain why on this slide. Okay. So in this image, we can see two different staining of fibers. This is a cross section of a piece of muscle, and we're looking down the length of those muscle fibers. The white or pale appearing fibers were your glycolytic fibers. And we're going to talk about why the other fibers are red. So your oxidative fibers, in contrast, these fibers rely solely on oxidative phosphorylation. And as a result, they're going to have many mitochondria. Okay, this only makes sense. This is the site of oxidative phosphorylation. They're going to have lots of myoglobin. What is myoglobin? It's a carrier protein. It's a carrier protein for oxygen found in blood. And myoglobin is what gives blood its red color. Okay, so because these fibers require oxygen, they're going to have more myoglobin. And having more myoglobin is going to make them appear red or pink or more fleshy. Okay, this is the basis of where we have dark meat versus white meat. If you look at a chicken, there's the dark cut of the chicken and there's the white cut. This is why, okay? The oxidative fibers need oxygen. They have more blood vessels. They have more myoglobin, more mitochondria, so they appear red or more beefy, whereas the glycolytic fibers do not need oxygen. Less mitochondria, less myoglobin, less capillaries, okay, and they appear more white, all right? And as a result of these being reliant on oxidative phosphorylation, they're going to be resistant to fatigue, right? Because we don't have lactic acid building up here.